Okay, all right, let's go through this real quick here. 7-step method. This is a process we use to graph a function accurately. As accurate as we can without just resorting to just using a graphing calculator, right? So, let's talk about the 7 steps. Now, yesterday we had 4 bullets, or I think it was, what, 5 bullet points?
Yeah.
5 bullet points. I'm gonna go through those bullets. I'm just gonna write them down right now so you understand, like, where did the 7 come from? Number 1, this is called end behavior. It's what we look at end behavior. There's 2 things in end behavior, so it's 2 out of the 7. We look at where the tails go. So it's an even and odd power situation, or odd power. And what that talks about is where the tails go. Are they going the same direction or opposite directions? The second thing we look at is the leading coefficient. And that tells me if my graph is going like up or if it's facing downwards. It's not just where the arrows are going the same direction or opposite directions, but which direction do they actually face? And that's something we got to get through today, because that's something I didn't discuss yesterday. We didn't do an odd problem yesterday. We just didn't. We did a function that had an even power for the front, for the highest degree. So we got to do an odd today. I said we were going to do one of those. Okay, so we'll look at that. So that'll be one of our problems out of the, I want to do at least 2 today, at minimum of 2. If we can do more, that'd be great, because I'm going to try to get through them as quickly as we can. So that was the first step we did. We spent a little bit of time, I talked about the rules. I'll go through those one more time when we get to our problem today. The second rule was called an X-intercept. Okay, it's where it crosses the x-axis. This is the easy one. The problem is that you need to know there's 2 things we check here. We check for, can you factor? Number 1, can you factor or quadratic formula, or is there a way that you can solve it so that you can actually graph? That's something we look at. But the second thing we look at is we look at this idea, it's called multiplicity. And this is something I hinted at yesterday, but we never saw it. It was something where a multiplicity test is when you have an x-intercept, are you going to pass through it, or will you bounce off of it? And that's something we didn't do yesterday. That's one of the new problems I'd like to cover today. So I'm going to try to cover it in a few problems here. Okay, questions up to this point? Now, if you were on Zoom yesterday, and don't fault you, maybe you didn't get a chance to watch the video again, or maybe you were just gone yesterday. You might want to get caught back up, obviously. The video should be online. I checked it this morning. It was there, so it just takes a little while to show up. And it is working. Things are working fine on that. Number 3, we talked about y-intercepts. There was only one thing you had to do with a y-intercept. You just had to substitute. You had to substitute 0 in for x. So substitute 0 for x's. That's all I had to do. Plug in zeros in all the x's and simplify. Okay. 4th rule that we talked about. This is called the Symmetry Test. I showed you the formal way the book does this. What a symmetry means is if your graph is doing something over here, and it's going to do the exact same object on this side. Like, will they look like perfect mirror images? Or will one side do one thing, and the other side do an opposite thing? That type of thing where it's not doing the same thing. Maybe this side just like ends, but this side goes off. That's doing 2 different things when we compare it to the y-axis. That's how we look at it. So sometimes it's just nice, is it supposed to be perfectly symmetrical? Do I need to draw the exact same looking curve? That type of thing. There's an easy way to check it. I have a shortcut for that, and that's the shortcut I want to talk about today. So we'll get to that. Hopefully I can get to one of those. And the last type of step was the turning point test. The turning point test. That tells me how many times does my graph change directions. So will it oscillate up and down a bunch, or will it just change direction once and kind of go up towards infinity? That type of thing. So these are my 7 steps. Now I know you're saying more that it's only got 5 bullets. Or 5 numbers. These are individual checks out of the 7. So 1, 2, 3, 4, 5, 6, 7. There are 7 items we look for. Questions with the list. Okay, I think we just need to put it into practice. I think that's what you need to see. Hopefully it will be a little bit easier for you once you see it actually working. Okay, so let's walk through a problem. I'm going to do one with an odd, because I did promise us yesterday we look at an odd problem. Plus 6x squared plus, let's go with plus 9x. Let's do that. All right. Okay. So this is one I promised you yesterday. Do we agree that it's just a random polynomial provided to you? Okay. And we're going to try to graph this thing without a graphing calculator. You know, and I might ask for one of you to go on Wolfram or Desmos and type this in and see what the graph looks like in the very end. So see how accurate we were. Because honestly, I don't know what this thing looks like. I can get an idea from this stuff. I've never done this problem before. So, okay, are we ready? Okay, so let's start here. So the first step, we have to figure out, you know, what direction my tails are going to face. They're going to face the same direction or opposite. That is end behavior. So that's going to be my step one. So step one, end behavior. Which direction are they going? Opposite directions. The reason why, I have an odd power for the highest degree. It was a power of 3. Okay, that's my degree, right? The degree was 3. So since it's an odd power, the highest degree, right? The highest degree was odd. That means my tails are going to go opposite directions. So the tails, right? The outside tails. I don't care about the middle. The middle we fill in later. I'm talking the outside tails. They're going to face opposite directions. Now, what I have to check, so that was the first step, figure out if it's even or odd base power. It's odd. The biggest power is 3. Now we look at the leading number out front. What was my leading number in front of the x cubed? 1. That is a positive number. That is a positive coefficient. So that means that we're going to travel not just up, we're going to go in the normal direction. Now I know you're thinking, what does that mean? Odd powers, odd base functions, odd base polynomials with the highest degree that's odd, have a certain particular direction they all face. And so since it's a positive coefficient, we're going to face the normal direction it would face. If it was negative number out front, like a -1, it would face the opposite direction. It would just flip the graph over. That's all it does. So here's what an odd base function looks like. The tails face opposite directions, like you guys said, because it was an odd base power. And this is the normal look. The left side goes down towards the left, and the right side goes up to the right. That is a normal odd base power. Notice, I didn't fill in all the arrows in the middle, because I don't know where it's going to go. I'm just telling you the outside tails are going to face those directions. Does that make sense so far? That's the step one. That was just step one. Evens, powers, or odd. That tells me where the tails face. If it's an even graph, the tails face the same direction. If it's odd, they face opposite. And if it was a leading number that's positive, they face normal directions. Either up, to the right, that type of thing. Okay, step 2. I'm going to go through this quickly. Yesterday we spent a little too much time talking about each rule. Unless you have questions, then fire away, please. Okay. Step 2. We need to look at the X-intercepts. We have to factor this thing apart. We have to pull it apart and see what the factorings are. So, on this problem, let me get rid of the 1 here. How do we factor this thing to start with? What are the rules? How should I factor that thing? Do they share anything in common? Yeah, let's factor that out first. What does everything have in common? An x. We're going to factor out an x. So that's going to leave me with an x squared plus 6x plus 9. Okay, so far that was a common factor, right? We did that. Is there anything I can factor inside that parenthesis further? Trinomial rule, right? So this can go further. It is a trinomial rule. Okay, so for the trinomial rule, we're going to they're going to be the same operation. They're both going to be plus signs, right? That's what the plus sign in the back tells me. They're the same, and then I have to look in the front. What are they? They're both pluses. I break up the x and x, and how do you break up 9? 3 and 3, and that will make the 6 in the middle, so that's good. So this is the factoring. Now, here's the weird part. 2 of those parentheses were the same. That's interesting. Didn't have any of that yesterday. So that x plus 3, there's actually 2 of them. That's kind of nice. I'm going to combine them, use a little law of exponent. You don't have to do that, I just like to write it like that, so you can see that there is 2 of them. Okay. All right, so we factored this thing apart. So now we got to read off what my x-intercepts are. So if you don't remember the rule from yesterday, how you check for x-intercepts. Okay, we factored it. Boom. Now we have to solve it. So you have to set each of these things, if they're variables, which they are, you set each of them equal to 0, and you solve. So if I set this equal to 0, what would x be? 0. If I set this thing equal to 0, what would x need to be? -3. So there's 2 x-intercepts. There's 0 and a -3. Yes, the x on the outside has a number. I set equal to 0 and solve. Well, there's no solving, it was just x was 0. If there was a number out front, like a digit, not an x, then you wouldn't do that. You only do it with variables. You set anything there with variables equal to 0 and solve. My shortcut I told you yesterday is if there's anything in a parenthesis, just pick the opposite of that number. So if it was a 3, it's going to be -3. So those are my x-intercepts. I'm going to go put dots there. 0 and -3. So there's x-intercepts. So that's why it's nice to factor. I'm already starting to figure out the middle of this graph now. Okay, now we're not done yet. We factored, we figured out my x-intercepts. Perfect. Multiplicity. Now we got to figure out, are we going to pass through or are we going to bounce? So that's what we're going to check. So that's multiplicity. So how you check multiplicity, you look at each x-intercept after you factored. What is the power on this item? What is the power on this x? 1. Okay. If it is an odd number, you are going to pass through that x-intercept. So any odd power will pass through. If it is an even power, that's an even, you are going to bounce off of that x-intercept. So you will pass through the 0 and you will bounce off of -3. Okay, does that make sense now? I look at the powers. I don't think we've seen a multiplicity of an even number yesterday. I don't think I did any of those. So you get to see your first one where it bounces. So I look at the powers tell me that. If they're all odds, I'll pass through every single one. If they're all evens, I'll bounce off every one. That could happen. Okay, so we're done with the x-intercepts. I've already figured I'm going to pass and bounce, so I can kind of go from there. Now, y-intercept. I have to plug in zeros for all the x's on the original problem. We go back to the original, so I'm doing step 3 now. Right? So if I plug zeros into all my x's, what would that thing turn out to be? If I plug zeros in all, what would it turn out to be? 0. Your y-intercept is 0. So duh, 0, 0. You pass through the origin. Duh. This is the x. You have to plug zeros for all the x's, and what you're doing is you're solving for y. Right? I plugged in zeros all the x's, and y ended up being 0. If it ended up being a different number, fine. Go find that number on the y-axis and put a dot there. I already have a dot where the y-axis is. It's right here. I already had a dot there. So I don't need to go put a different dot. So the y-intercept is easy. Plug in a bunch of zeros, solve it. It should be super quick. It's usually just whatever the back number is. That's just the trick. Okay, symmetry test. Is this thing going to be symmetric from the left side to the right side when you look across the y-axis? I can already tell you it's not. What gives it away that it's not symmetric?
The x-intercepts.
The x-intercepts. They weren't perfectly balanced. If it's going to be symmetrical, like having the same thing on the left side and the right side, you would probably hope that the x-intercepts will probably be balanced. Like there'd be a 3 over here, maybe a 3 on this side, so that maybe I'll do the same things. So it's definitely probably not symmetric. Now there's a rule for checking it. The book says you're supposed to plug in a bunch of negative x's into the original problem and simplify the thing down. That's just a bunch of waste of time. Here's the easiest way I can figure out what type of symmetry it has. If it's even, odd, or neither. If it's even symmetry, all the powers would have to be evens for all of your variables. Are all these even powers for your variables? No. Are they all odd powers? No. So it's a mixed bag, so this thing is not symmetric. Now, for those who are at home and or maybe you're here and you're like, yeah, I don't understand that. I don't understand what even and odd symmetry means. Let me give you an example. Even symmetric. So if all your powers were evens, your graph would look something like this. So if it did a little camel hump over here, it would do the same camel hump on this side. It would be perfectly symmetrical, like the exact same thing. If it went up this way, it would go up that way. That's even symmetric. They do mirror images of each other. That's even powers, if everything was even. Odd powers, if I did something over here, it would do the same thing on this side, but on the flip. It would be diagonal. It wouldn't be across. It wouldn't be over here. That would be even. It would do it diagonally from it. So if it went down, this side goes up. It just does the opposite. That's an odd power. So if all the odd powers were in there, it would do something like that. And it makes sense. The tails go different directions. And if it's neither, they do different things. So maybe one side does a little hump and the other side goes straight. You know, so ours is ours is neither symmetrical. So because you can see the powers. So that was a little shortcut I give you for symmetry. A lot of people don't even think about that. Turning point. Turning point test. So this is the last rule. So we already figured out that this thing is not symmetrical. Not symmetric. Okay. The final step, rule number 5, it's technically the 7th step. How many times does this thing turn directions?
Once.
Yes, you're right. Here's what I'm saying. You take your highest degree. We already said it earlier, the very first step. What was your highest degree? Well, it was 3. You always subtract 1 off of it. Whatever your degree is, you always subtract 1. Whatever that number turns out to be. This is how many times your graph will change directions. So my graph started in this bottom left corner. It will change directions once and twice, and it should go off. Okay? That's what it's going to do. It'll change directions twice, and we'll see that here in a minute. So that tells me if I did it right when I'm drawing it. Okay, I think I got everything I need. I got all my intercepts. I figured out if I'm going to pass through and bounce. I think I kind of figured out what I need to do. It's not symmetrical, so I don't care about the graph. I don't need to make it look pretty. I figured out my y-intercept. I already have that. Turning points, hopefully if I do this right, it'll look like it's changing directions twice. Okay, are we ready to go here? Ready to fill in the middle? Okay, it needs to bounce off the -3 x-intercept. So it has to bounce off a -3 for the x-intercept. So I'm going to go up, so this arrow's going to come up. It's going to bounce off a -3. So just like bounced off of it like a little bouncy ball. And then it's going to pass through 0. So at some point it's going to change directions and then pass through 0, and then the arrows will end up going up. And so the arrows did actually face opposite directions. And did it change directions twice? Yeah, it was climbing here. As it went from left to right, it was climbing. I know the arrow is facing down, but it is climbing. Changes directions once and twice. So yeah, it did its job. And it's definitely not symmetric. The left side and the right side of the y-axis do not look the same. Questions? Now, does anyone have like a little Chromebook that they can open, like you're really quick at like Googling? Go to Desmos if you can. I want you to type in that problem, Desmos. So type in x to the 3rd. Again, you have to use a little like shift number 6 key for a little up arrow. Put enough powers in it. Type that in, y equals x to the 3rd plus 6x squared plus 9x. And let's see, I think that should be the graph. Now the only thing, the question we had yesterday was, and I think in both classes even asked it, where is that little thing at? Little turning point. That we don't have yet. I haven't shown you the rules to figure out where did it change directions. That, I'm not joking, will take me a better part of 2 classes to explain how to do it correctly. So I'm not going to do that today. It will take a long time. Just have the idea that it changed directions. I don't know where on this problem. We can show you that later. Does it look right?
Yep.
Yeah, there you go. So look at that. So it does look like that. Like his dipped a little bit lower at this middle area. How low did this thing get? It looked like it went pretty low.
-4.
Oh, so yeah, it was pretty close. So it dipped to -4 and then went back up. So the graph, if you didn't see it, it looked just like that. So pretty good. Pretty good at accurate drawing for not having your graphing calculator. All right. Now, here's my question to you, because I want to do another one, right? Or at least 1 or 2 more. Do you guys want to see one that's like maybe symmetrical to see kind of what would happen if it looks the same? You guys want to see one of those? Okay, let's do one of those. I can make an odd or even. Does it really matter? What you want to see?
Odd.
Odd. Okay, let's do an odd perfectly odd symmetric. Okay, so it'll do opposite things. Okay. So this will be our second graph today, probably your fourth graph if you were taking all the notes from yesterday. All right, let's do an odd base symmetrical graph. Okay, so let's do something like, let's go with 4x to the fifth plus 4x to the third plus x. This will be my graph. Okay. Maybe we'll do another one if I can go through this pretty quick. Hopefully this will make sense to you. I should throw in the negative signs in there so it looks a little bit prettier. We'll go with it. I'm going to stick with it. I like the idea. All right. We ready to go here? All right. Again, I don't know what this thing's going to look like. I just literally made it up. Not bad. So let's walk through the steps here. Okay. All right. First step. Where are the tails going to go? The end behavior. Are they going to go up, both of them down? They're going to face opposite directions. What do we have?
Opposite direction.
Opposite directions. It's an odd power. Now, is it going to be a normal graph or is it going to be a flip? Well, that's where you have to look at the number out front. That number was positive, right? So it's going to go the normal direction. So the upper right corner is going to go up here. The lower left corner is going that way. Right, that's an odd power. That's what normal odd powers do. If it was negative, like that was a negative 4 out front, the arrows would change direction. So this arrow would go up instead, and this one would go down over here. So it would just flip over completely. So, okay, so far so good. That was end behavior. Boom, we figured it out. Tails go opposite direction because the odd power is power 5 on this thing. Okay, X-intercepts. We have to factor this thing apart. Okay, we have to factor this thing. So is there anything I can take out here in the beginning? X. Let's pull out an X. So we got to factor this thing apart. So if I pull out an X, that's going to be 4x to the fourth plus 4x squared plus 1. Because I divided everything by an X. Notice the plus 1 in the back. That always messes people up. They always forget. When they divide, you have to have a 1 back there. Okay, so now this thing can go further. I know it doesn't look like it. It is a trinomial. It just has weird powers. That's fine. It is a trinomial, so we're going to try it as trinomial rules. It's going to be a plus and plus. It's going to be a 1 and a 1. And how do you break up a 4x to the fourth? What? 2x squared and 2x squared? If I go 2x and 2x squares, that should make the 4x squared in the middle. And if I multiply that, I'll make 4x to the fourth up front. Yeah, that should be it. So if you FOIL it out, it does make the thing in the parentheses. Again, I broke up the x's evenly and broke up the 4 so that I could make the 4 in the middle. Notice the 1 didn't just make the 4 in the middle, but the 4 out front did as well. So I had to FOIL it. Okay, so that was the factoring of it. I can't go any further. These are not difference of squares, and it's not cube rule or anything weird like that. So we have to set each of these equal to 0 and see if it actually has a solution to it. So if I set this x equal to 0, what would the x-intercept be? 0. If I set this thing equal to 0, would it make a number? And it does not. There's no x-intercept for that. Here's why. If I subtract the 1 across, and then I divide by the 2, there's no way you can square a number and get a negative half. You can't square a number and get negative. So this is an imaginary number. So there is no x-intercept for that one. So it's imaginary, there's no x-intercept. And this one, the same thing, it's the exact same problem, so there's no x-intercept. So on this problem, there's only one x-intercept. That one, 0. It was just for the x out front. The other two didn't have any x-intercepts, they were imaginary. That's fine, it can happen. You don't have to have that many x-intercepts. Just we have one at least. Multiplicity of it. Will I bounce off of it or will I pass through it? What was the degree on my one x-intercept? That was a 1, right? So I'm going to pass through this one. So I'll pass through that one. So somehow it's going to pass through. It's probably going to do this. Probably going to go through like that and kind of go up that way. Probably what I'm expecting. Okay? So far so good. Okay, and now we did the x-intercepts, y-intercept. If I plug zeros in for all these x's, what would your y-intercept be? 0, duh. We went right through the origin, and that's a y-intercept. So that one's good. Symmetry. Do we have all evens or all odd powers? All odds. This is an odd symmetric problem. That means the left side over here, whatever it does, it'll do a perfect mirror image over here on this corner. They're going to be kitty corner from each other. Okay? So whatever I draw here, I have to draw the same thing over here, the exact same look to it. It'll have the same numbers. It'll just be perfect images of each other. Okay, so we'll do that here in a minute. I'll make sure the graphs look okay. And turning point test. How many times should this thing change directions? Okay, all right, we'll keep going here, sorry. All right, so this thing is going to change directions 4 times like you guys said, because you take the highest degree and you subtract 1 off of it. So it should change directions 4 times. So that means it's going to oscillate kind of a couple times. So it'll do something like this. This is what I'm expecting. It may not be perfect and it may not be great, but this is kind of what I'm expecting, okay? I'm expecting maybe it'll do something like this, and then it will go right through that x-intercept and up here. And then whatever it did, it's going to do the exact same looking graph and then kind of go off. That's kind of what I'm expecting. Now, it doesn't have to. That's something that you also need to understand. So it's an odd-based symmetry. So odd means, they're going to do the same thing in the corners from each other. Now, the turning point test is the only iffy problem. Okay, turning points. Your graph does not have to turn. It doesn't have to change directions. That's something that you need to get used to. Sometimes it doesn't. It's just an idea that at most, it will change directions 4 times. It could just change directions once. Okay. Maybe it just did a slight. Maybe it just did a slight like flattened through, and then it kind of took off. It just, in theory, it would change directions up to 4 times. So I don't know about those little bumps. They don't necessarily have to be like that. So did anyone type it in Wolfram? Or okay, type it in. Let's see. I don't know. I think I'm exaggerating the little like bumps in the road. But if there is any bumps, they have to look the same. I know that. Did it look okay? So it's more flattened in the middle, didn't it? It just kind of did one of these. It kind of just went through. It didn't really do these kind of changes. It kind of just did one of these, kind of flattened, and then just kind of took off. But this side and this side looked perfect mirror images from what I could tell. It was kind of doing the exact same work as it went. This graph and that graph were just like flips of each other. So, if I probably added more like variables in there, like more numbers, it probably would have done the more like really exaggerated changes what mine did. But this is in theory. And again, if you're thinking like on the test, like how do you do this stuff on the test? You do it like this. You make an educated guess what it will potentially look like. You could be wrong, like I was wrong, right? I'm making an educated guess what it could do, right? And then we would use the other test to figure out would it actually have like peaks and valleys. They're called turning points, like where those inflection points happen. Those are the things we do in like the later sections. All right, questions? All right, I'm going to give you your homework today. Now, we are going to do a couple more of these tomorrow. I want to practice more because obviously just giving you just a few of these isn't probably enough. But I do want to at least give you a little bit of time if you want to try it out by yourself. So we'll do a couple more examples tomorrow. I want to do an even, like, kind of symmetrical problem. It's 4 problems front back. It's due on Friday, so I have a couple days to do it. When you're going through and doing the 7-point steps, try to write down like what you're looking at, what you're doing. Like what your degree is, what the x-intercept would be, what the multiplicity would be. Try to be very specific off to the side, so that when I go to your graph, I can see why you drew it the way you did. But again, we're gonna do more of these tomorrow, so don't like go, oh my gosh, I have no idea even how to start this. We're gonna practice more, it's due on Friday. I just want to get it in your hands, because maybe you're ready to go. I don't want to hold you back, but maybe you're not, so we'll do a couple more tomorrow. But we've only got like 5 minutes left of class, and I want to at least get it in your hands here. So what you're doing is you're kind of drawing this, right? You're trying to figure out, where this thing goes. You'll have to know your different types of factoring. I try to pick problems that are factorable, right? Where when you did the end behavior, you figure out where the tails go, right? But then when you get to the part where you factor, everything should be factorable. It's either like a common factor, or a grouping, or a difference of squares, or trinomial. They will be factorable. So you just have to like kind of mess with the numbers until you can figure it out. Then, there'll be some type of y-intercept in your problems. You'll have to check for symmetry. Some of them could be, odd, it could be a neither, it could be an even. I think maybe tomorrow, one of the first examples I'll do an even symmetric problem, so you can see what that graph would look like compared to this one. And maybe I'll pick a problem tomorrow where the turning points are really exaggerated. You can really see kind of what's going on there. That's it for today.